This video is a brief introduction to the idea of frequency distributions and their graphical representation as histograms. It's not going to be on Math Studio applications, but just the definitions regarding those subjects.
In some of the previous videos, we have been talking about frequency distributions and histograms. But what is a frequency distribution? Consider a data sample X as a collection of data, for example, a matrix of n elements, in which we have identified our minimum and maximum value. Now, suppose that we want to classify that data, which is all located in these points between the minimum and the maximum value, into a number of bins or classes. And so we select so-called bin limits that will be a certain XB minimum and XB maximum to classify our data within those limits. And so we see that there are four possibilities here. The first possibility is that the XB minimum is less than X minimum and that XB maximum is greater than X maximum. Another possibility would be to have the XB minimum be smaller than X minimum, but XB maximum being larger than X maximum. Third possibility, XB minimum smaller than X minimum, but XB maximum is smaller than X maximum. And the fourth possibility is that X minimum be larger than XB minimum and X maximum be larger than XB maximum. These possibilities bring us to the following conclusions. First, in case one, we have all data contained in the bins that we have defined. If we follow case two, there will be some points below the XB minimum, and so some points will be left out that correspond to points smaller than XB minimum. There is the possibility of the third case, in which case some points will be left out of the XB maximum. Finally, if the XB minimum and XB maximum are within the X minimum and X maximum, there will be points below and there will be points above. All these points, when we use that classification, are called outliers. The selection of XB minimum and XB maximum is kind of arbitrary, but I wanted to contemplate all those possible four cases. Once the XB minimum and XB maximum has been selected, we can define the bins where we're going to classify data in the following way. We could have them equally spaced, in which case we can give the bin width and then calculate the number of bins, or bin limits actually, as XB maximum minus XB minimum over delta XB plus 1. It is possible that this number not be an integer, in which case we'll have to select a new MB close to an integer, an integer value, and then recalculate the upper limit in this fashion. Another possibility, if we go for equally spaced bins, will be to give the number of bin, in which case we're going to calculate the size of the bins, the bin width, and that will be a fractional value, and it's fine. And then we're going to proceed in either case, whether given this or given this, we're going to proceed to calculate the bin limits following this algorithm. Now, suppose that we take our sample X of n elements and think of the bins as these boxes where we're going to be putting data. And so we have that if the X minimum is below the XB minimum, the XB1, then, or if X maximum is greater than that, we're going to have outliers, both outliers less than XB1 or greater than XB, and this will be the most general case. And then what we're going to do is that take each XI and locate it in a bin so that it will be between the lower and upper limits of the bins. So we have these limits that will define our different bins. And so if a particular value it's located, let's say, between these two, then we're going to put the value in here. If then we find one in here, we put it in there. And when we keep doing that, and we're going down through all values in our sample, then we're going to have accumulated there a number of data points in each one of those beans or classes. And we have a number there that follow the bean numbers. You have numbers F1, F2, F3 that are called the frequency count. And basically it's just how many values are contained in each one of the beans. And so now another thing that we can do is obtain the midpoint of each bean. This is called the midpoint or class mark. We have the frequency count and we have the beans. And we could plot the number of count of the bean count, the frequency count against the bean and produce this figure, which is called a histogram. Now the data from the histogram can be represented in a table called the frequency table. And that data includes the bean number, I'm going to call it K. And then we also have for each bean, we have a lower limit and an upper limit. The left bean limit and the right bean limit. And as you can see, this number gets repeated here, and this number gets repeated here, and this will be repeated here. Because we're just moving from one bean to the next one. We could calculate the midpoint, which is just half of the sum of the extremes of the interval of the bean. Then we have those data values and the frequency count, which is the number of data points in each bean. And these two sets of data correspond or provide the data for the. Then we can calculate what is called the cumulative frequency, and all what it is like the cumulative frequency for the first value is just the same as the frequency. And then we go adding this cumulative frequency plus the frequency to the left gives me the cumulative frequency 2. So basically the cumulative frequency is the count of frequency up to the current bean, accounting for all the previous beans. Then the sum of the frequencies represents the number of frequency count, the total number of frequency count, which may be different from the number of data points if we have outliers. The relative frequency is the frequency count divided by the number of data points in the frequency count total, which will be given as a fraction. And also have a cumulative relative frequency, which is like in the case of the cumulative frequency is just copying this one to here and then adding and keep adding in that fashion. And so it will be the cumulative frequency relative to the total number of data points. Once we have the histogram, we may be wondering if the data shows a tendency to be normally distributed, normally being the normal distribution from the continuous distributions. In which case we can show a graph with a normal distribution by taking the total area under the rectangles of the histogram, and that is calculated using this formula. We simply take the frequency in each interval, which is the height, that's okay, multiplied by the width of the interval, which is the being position to the right, at interval k minus the beam position to the left. And so the product of all these, the areas of all these rectangles, will give me the total area under the curve, under the histogram. What we need to do now is form a modified probability density function in which we're going to take, actually we have a missing part in here. We're going to take the PDF of the normal distribution and multiply by the total area. What are the parameters of that normal distribution? Those will be the mean value of the original data set X and the standard deviation of that data set, which is information that could be easily found. And then we can proceed to plot in the same set of axes the histogram and there's a missing part in here, the modified PDF, and see if this curve follows pretty much the histogram. It's kind of a visual way to check about the normality of a histogram. And with this, we finish this presentation about frequency counts and histograms.